The second theorem is about the law of large numbers. So the law of large numbers, what does it mean? It's very simple. It says that when you have a sample, okay, that will grow, okay, when you have a sample that will grow to a large number, then the mean is going to converge to the population mean. The sample mean will converge to the population mean. The average of result from a large sample converge to the expected mean as trial increase, as the data set increase. The sample averages approximate the population mean with a large number of trials. Okay, so it means that when the data set size increases, look now, if I have a sample of only 50, look at the average. Now it's 26, then I increase the sample by 10. It becomes below. So there is a variation. You see the variation? It's big. And I worked on small samples. You can look when I increase the sample, look at the variation. It's becoming smoother, until now, if I go beyond that, because I have only 350 values, I'm going to reach to almost constant. Maybe not constant, but it's almost constant. And this is why we have the weak law and the strong law. And the difference between both is how confident we are about the convergence. In the weak law, in the weak large law of large numbers, the convergence is probabilistic. It's likely. Okay, as the sample size increase. When we have a strong law, it's almost sure to converge. We have more confidence to converge to the expected value. So this is the difference between the weak law and the large law. So from mathematical perspective, it means when the sample size increase, this probability, okay, this probability significantly deviate from the population means diminish. So it's likely that it's going to convert to the population mean. And here, it's almost sure that it will converge to the population mean. And this depends on how large your data is. For example, now, I would say here that I have a weak relation of the law of large numbers because my sample data isn't big enough. And I'm going to illustrate this on the weather data set. Look now. Now, analyzing the temperature reading in Riyadh in 2018, we're going to do what? We're going to calculate the average temperature for a certain population or for a certain sample size n. Now, with the continuous sample n increases, I will have the average value of the temperature, the empirical average value, will converge to the true mean value of the city. Okay? This is if this sample size is going to increase indefinitely. And if it is not going to increase indefinitely like here, so we will say that we have a sufficient sample, okay, to estimate, to have a good estimate, probabilistic estimate of the population mean.
So it will be weak.
Yes, it will be weak. And this depends on how large your data is.
So the difference between the strong and the weak is the size?
The size of the data, yes. And these actually, the both laws underpin the reliability of statistical estimates for large data sets. This is why we have confidence on the statistical estimates and the statistical convergence when we have sufficiently large data. If we don't have this theorem, if it is not proven, we cannot say that any model in machine learning or deep learning is sufficient to be generalized. It's about the generalization, the ability to generalize the model to unseen data. Because the population contains your data set, your sample, and some unseen data that you will do the inference on. Yes. And this is why when we train machine learning models, we have the data set, this is our sample. This is what we will train our model on. And we will use the test data, it's unseen data, so later on we're going to test it on our model to see how close the prediction will be on the unseen data. If we find a big gap, it means that we don't have a real convergence of the law of large numbers. Maybe our data set is not sufficiently large. And there are other considerations as well, like regularization. There are things inherent to the network architecture, and there are things related to the data set. But the first thing that we'll need to think about, try to increase the data set. Just remove the data set from as a hyperparameter that will affect the convergence. And if you increase the data set sufficiently and still you have issues, in this case, you need to look at your model design, not the problem from the data set perspective. Is that clear?
How do you ensure, doctor, if the model has problems?
That's always trial and errors. Yeah, you need to make experiments, draw conclusions, check whether you have any issues, and then you will decide. It's a complete engineering problem, okay? But this law actually governs that if you have sufficiently large amount of data, in this case, your model is going to converge to like the population, to the population performance, yes, for the model. And this is implementation in Python. Okay, you have this notebook. I'm going to share this notebook. It contains all the examples. Okay, it contains all the examples. Look now, this is what we've done. We have the weather data set, and we have 350 values. And this is a function that will start from an empty list of sample means. And we're going to take the sample size plus an increment and the length of all data to go through all the data. Now, the start sample size is 10, and we are going to increment by 10. I will take 10 temperature, make the average, and then 20 temperature and make the average, and then 30 temperature and make the average, and so on. And this is what we have done. Look now. We take the average on from 0 to the sample size. The sample size is going to increase with time. Okay? The sample size is going to increase. Start from 10, 20, 30, 40, 50, and so on. And as it increases, look at the values. Started from 20, 26, 24, 25, 25. Finally, it converts to 23. Okay? And this is the sample size. Look at the sample size. It's increasing by 10 in every iteration. Okay? Now, for sample size, starting from 10, starting sample size, to the length of the data, last value of the data, the sample size, 350. And you have an increment of 10 in this particular case. Calculate the sample mean and then put the sample size. Now here, I have the sample size, and in the y-axis, I have the average value calculated for that sample size. And as the sample size increases, what happens? The average value converge to the population value. Still, I didn't reach the population value here. Okay? And the good thing is that the next theorem will tell you these averages have normal distribution. So I can estimate what is the variance. And this will give me the confidence I will have on that mean value. شفتوا القوة بتاع theorems كيف؟ You will see this tomorrow when we talk about the central limit theorem. All these averages, they have a uniform distribution. This means I can calculate their average, the average of the average, and the deviation from the average of the average. And this will give me a better estimate of the population mean. Yes?
Realistically, we don't have the population values, huh? We don't have the population.
We don't have. Like, we can have how much I am deviating from the population value based على الفارينس اللي عندي على average of the means. Okay? And that will be the next topic to close.